Hello everybody, welcome to this course on natural language processing, which will be a series of videos, some of which will be concept illustration and some of it will be hands-on using R. So by way of introduction, I am Arindam and I have about 12 years of experience in data science and super passionate about this field, and you can call me an enthusiast as well. Why am I creating something like this? So if I just give a brief overview of that, and it takes me back to my experience when I was trying to get familiar with some of the concepts of NLP, my early days with NLP, and obviously I was in the hunt for some of the training resources which were available at that point in time. So one of the things I realized was that by and large, the training resources on NLP are of two types. The first one would, go into a lot of in-depth theory, the stats and the maths behind these concepts, but not talk a lot about the implementation areas. And the second one would basically give you R or Python scripts to run and get some results. So what I didn't see much was a blend of these two, and my personal feeling was that it is this blend which is what people look out for, particularly people who are working in the industry and want to learn things and apply in their business problem. So, motivated by this thought, I planned this training, which in which I have aimed to keep a blend of both the theoretical, the conceptual, and the intuitive aspects as much as it is required to implement these algorithms, and also covered some of the hands-on implementation of the NLP techniques using R. So, if you are opting to go through this series of videos, then what is in it for you, right? So the goal of this training is to equip you to solve most of the NLP problems. Now, yeah, just like any other field, NLP is also a pretty vast field, and it would be kind of a overstatement to say that we are covering everything over here. We are not doing that. So, but having said so, what I've tried to do is I've tried to include most of those concepts which you will end up using more often than not when you're solving your business problems using NLP. And in terms of prerequisite about NLP, it's none, and it's indeed none, so you can trust on that. So we start from the very basics of NLP and then try and build upon those concepts and go into more intricate things. And but there's a little bit of familiarity required with R because we will be doing some of the hands-on implementations using R, and then a little bit of idea about supervised and unsupervised learning using numeric and categorical data would also be helpful because not because we would be doing them here, but in some of the sections we would possibly be drawing analogies with something that we do with numeric data or with categorical data. So this is how the overview of the course looks like. So this is a series of videos and you'll have to be really patient to go through all of them, but then there is a very sequential and logical build up to it, so you can do it in your leisure, and the only thing will be, if you keep doing it with a certain periodicity, then you'll not lose the context. So we'll start off with the very basics, as I was saying. So there is no NLP prerequisite required whatsoever. So we start off with how do we organize text data, which is inherently unstructured, into a structured format, and then we do some hands-on for that structural representation of text data, and we then talk about how do we do exploratory data analysis using text, how do we visualize those results, and what is the interpretation of those visualizations, and then we talk about term frequency, inverse document frequency, and then go into more intricate topics, more complex topics like the vector space model for texts. How do we compute similarity between two texts? Then how do we do topic modeling, which is basically text clustering using latent rich allocation. How do we do latent semantic analysis? So and for all of these, along with discussing the theory behind these concepts, the intuitive approach behind these concepts, we also do hands-on implementation of these using R. So with that, we are all set to start. So this is where we start off with, right? So why are we saying that text data is special? In the sense that we have to throw open an entirely new area called natural language processing, uh, and actually design a training on that. So why is text data special? Why can't we analyze text data in a way similar to we deal with numeric data or categoric data? So this is a very fundamental question to answer right at the onset, but at the same time it's a very basic and very trivial question as well, because if you see when you work with numeric data, or even if you work with categorical data, there are certain things that you almost always do, right? You do a distribution check, you do univariate analysis, then you do bivariate analysis, right? And you do different kind of visualizations of data, be it the histograms, uh, then the other bivariate plots like the scattered plots, so on and so forth, to find out what story is the data telling, what are the correlations between different pairs of data that you have now. And subsequently, once you have done all of that basic exploratory analysis, you move on to do supervised learning or unsupervised learning, building a model, doing some clustering, etc., etc. Unfortunately, none of these actually work with text data in its native form. With text data, you cannot do univariate analysis, cannot do bivariate analysis. You cannot even apply the supervised learning algorithms directly on text data, right? Because some of them, in fact, most of them, they use some concept of distance which cannot be applied on texts. So in its very native form, text data is not something which can be dealt with in a way in which we deal with numeric data or categorical data. So obviously, if we are handling text data, the first step should be to find out a meaningful representation of text data. And what would be a meaningful representation? A meaningful representation would be, something which can enable us to apply all the well-established data exploration techniques that we have been doing on numeric data for ages on text data as well. So if we are able to find out a representation of text data so that we can visualize text data, we can do univariate analysis on text data. We can find out ways of doing supervised learning or unsupervised learning on text data. Then that is exactly the kind of representation that we are looking for. So to summarize, the alternate representation of text should be such that all the elegant data science algorithms that we have developed over the years, they can be applied on text data. Okay. So we'll now go into the details of how text data can be organized in a structured format so that we achieve what we want to achieve. Okay, so fundamental question once again. So what is text? Text data is it's a collection of words, or you may say it's a collection of sentences. Somebody may say it's a collection of paragraphs, and all these definitions are valid, right? Now, if I ask a question in a slightly different way, that what is the most fundamental or the most basic component of text? Now, the answer can be alphabet, right? But then if I say that what is the most fundamental meaningful component of text, the answer perhaps would be words, phrases, or even sentences, because alphabets stand alone, they don't carry any meaning. So So fundamental meaningful components of text data, the most granular part perhaps would be word. If we go a notch higher, it can be phrases, and if we go even a notch higher, then it can be sentences. So sticking to the most granular decomposition of text, let's assume that for the time being, the most granular yet meaningful decomposition of text for the time being is words. So with that, let's take an example. So this is a text we see out here. It's a collection of 3 sentences. And what does it read out to be? This is a natural language processing training. It was real hard work putting the material together. It was indeed. And hope our delegates find this training to be beneficial. That's an honest confession. Now, it's a simple collection of 3 sentences. Now, what we can do is we can basically decompose this collection of 3 sentences into individual words, right? So this is a natural language processing training, so on and so forth. We can decompose each of the sentence into individual words. Once I have done that, what I can do is I can store these individual words either in the form of an array or in the form of some kind of a matrix, right? So I'm slightly getting towards a structured representation. Now, if you think of numeric data, it can be represented in the form of a 2-dimensional array or a matrix, right? So if you think of a table of numeric data, along the rows you will have the observations, and along the columns you will have the different variables that you are dealing with. So that's basically a 2-dimensional array or a matrix representation. So in text data also, by decomposing the individual sentences into standalone words, and then by storing these words in some kind of an array, we are conceptually moving towards a structural representation. We'll soon find out how that happens. Okay, so generally speaking, the first step if we are dealing with text data is something that is called tokenizing texts. Now, and as I was saying, tokenizing is basically the term for breaking down text into its most granular, meaningful component, which we defined as word. Words are also called tokens. So in the context of natural language processing, when we say tokens, it is to be interpreted as words, right? And but having said so, we can also tokenize big paragraphs or a collection of sentences into individual sentences. And when we are tokenizing text data into words, all that we are doing is we are basically segregating individual components based on wherever we see a space or a white space, right? Because typically in a sentence, 2 words will be separated by a white space. Instead of doing that, we can also say that we will segregate components of text data based on punctuation. So that will give us some kind of a sentence tokenization, but then that is not something that we will do most often. Most often what we will do is we will do a word tokenization, and there are processes available in R and Python, which can do tokenization in a fairly simple way. We'll see them when we go to the uh, hands-on part. So the first part is tokenization. Now, here comes the first of the board work that I was referring to, that I'll take resort to certain times in order to explain or illustrate some of the concepts. So focus on the left hand side of the workings out here, the one that you see in blue. So if you're dealing with numeric data, so you'll have typically have a framework like this, right? You will have observations, let's say you have n of them, and you will have features or variables. Let's say you have p of them, and then you may or may not have a y variable, which is the dependent variable. So if you are doing supervised learning, you might have a y variable, otherwise you will not have it. And this two-dimensional array or matrix, whatever way you call it, this is typically called the data matrix or the design matrix, right? And the ijth element of this matrix is nothing but it's the value of the variable xj, for the ith observation. Now we will aim to represent text data in a format or in a structure which is similar to what we see in the left hand side, because this is a familiar structure for us. Anything that we can represent in this structure, we know that we can work with that structure for implementing all our data science algorithms. So our target will be to represent text data somehow in this structure, right? So so what do we have in text data? We have a collection of words, right, which we say that these are the most granular meaningful components. Now for a moment assume that in the text data that you are handling there are n different documents. Now documents here would be observations. So let's say there are n observations and each observation is a text. It can be one sentence or collection of multiple sentences, whatever the case may be. And since you have done tokenization, which means you have basically extracted the individual words from each of those documents, you know what are the total number of unique words that you have across all the n documents or the n observations. So let's say the total number of unique words that you have across all documents is p, right? And then each such word becomes a column in this matrix, right? And this kind of a representation is actually called a document term matrix representation or a document feature matrix representation. So they are often abbreviated as DTM or DFM. So in the rows you have the documents, and in the columns you have the individual words of the tokens, right? And this is a very analogous representation to what we see in the blue section here, where we are dealing with numeric data. In this case, every row is every observation, whereas for the text data, every row is every document that we have, which is equivalent to observation. They can be one single observation, can be a single sentence or a collection of sentences. Again, in the left hand side, we see every column is actually every variable, and we might have a dependent variable as well, depending on the case. In the right hand side, every column is actually every word, assuming that we have p unique words in the entire data. So there will be p columns, and this representation, the data matrix for the numeric data or the categorical data, becomes the document term matrix or the document feature matrix for the text data. And by now it would be obvious to you that the ijth element of the document term matrix is nothing but number of times the jth word appears in the ith document, right? So there are total of p unique words. So if I look at the ijth element, it basically means that how many times the jth word, which is one particular word in the entire collection of data, how many times that word actually appears in the ith row. Now we have already run into a trouble out here. What is that? I am saying P here is the number of unique words that we have in the entire data. Now think of it, if you have a collection of let's say not much, 100 sentences, right? And let's say these sentences are about review that customers have written, users have written about some of the Android apps, right? So you'll see that the number of unique words, even with 100 different reviews for any Android app, will be huge. So P here will be significantly larger than what you are typically used to seeing in terms of dimension when you are dealing with numeric data or categorical data. So obviously what happens, the first problem that we face here is that this matrix becomes very high dimensional, at least with respect to columns, if not with respect to rows, right? Because you are dealing with text data, and every column is basically representative of every unique word in the data. The other problem that you will see is this matrix will be very sparse, in the sense that there will be lots of zero entries in this matrix for the text data representation for document term matrix. Why would that be the case? If you think intuitively, even though the number of unique words present in the entire data will typically be huge, but in one single document not all words will be present, right? Only a few words amongst the total collection of words will be present in one single document. So if you go row wise, you will see that in a given row there are lots of zeros, and only for the words which are present in that document you will get some non-zero value, which is basically the count of the number of times that particular word appears in that document. So two problems we have already encountered. One is the problem of dimensionality, where we are saying that the number of columns in this matrix will be huge, and the other problem is this will be a very sparse matrix and lots of zero entries, right? So this is how a general representation of a document term matrix or a document feature matrix will look like. Along the rows you will have the documents, and along the columns you will have the unique words or tokens, and typically this will be a matrix of huge dimension, and the uh, dimension will primarily be driven by the factor k here, which is the number of unique words that we see, right? And of course this will be a very sparse matrix. So so at this stage, I think what I will do is I will quickly introduce the data that we plan to use throughout this course. So this data is basically a data of product reviews from Amazon, which has been made public for NLP related research and understanding. And there are a total of 1,000 reviews, 500 of which are positive reviews and 500 are negative reviews. So the data actually has two columns. The first column is the review itself, the text that the consumers or the buyers have written down in terms of the review, and the second column is the is a label which says positive negative, which can be labeled as 1 0. So if it is a positive review it is 1, if it is a negative review it's 0. Okay, so that is the data that we'll use. We'll actually have a look at the data when we do the hands-on, but that's the data that we will use for illustration. Now uh, this is a snippet of code. We'll do the hands-on with this code in the subsequent video. So all that we are doing is, in this snippet of code, we are reading in the data and then we are doing some very basic stuff. The reason I introduced the data right at the onset is because I want to show you something very interesting here. So in this graph, what we are doing, the visualization here is we are basically calculating the length of the positive and the negative reviews. Okay, and when I say length, we have already done tokenization. So we are counting the number of words in each of the sentences, and then we can actually count the number of alphabets as well. That would also be directionally the same. We are counting the length of each of the sentences and then breaking it up by whether it is a positive review or a negative review, and then plotting the histogram of that. So without doing a lot of NLP, just by doing basic tokenization and then counting the length of the individual reviews, we see that something very interesting and very intuitive as well. We see that wherever there are negative reviews, the length of the reviews are generally much more than wherever we have positive reviews. So it's very common human psychology. Like if we like something, we we may just explain it in a single sentence saying, "Oh, the product is great," or "the product works fine." But if we don't like it, then we really write a lot about, that what is not working, and then we really vent it out. So that human psychology, human behavior is getting exhibited in this visualization as well. So this has got little to do with subsequent NLP uh, techniques and approaches, but there's a very interesting observation that I actually got from the data that we will be using here, and hence I thought I will just share with you right at the onset. Okay, so till now we have just done tokenization and we have achieved that this visualization and having some very intuitive insight. Now, okay, so this is another snippet of code which gives us the document term matrix or the document feature matrix. It calculates that. Okay, we will do the hands-on with this as well in the next video. Okay, now this is important. So, as I was saying, that one of the trouble that we run into when we construct a document term matrix or a document feature matrix is the fact that it has huge dimension, primarily driven by the huge number of columns, because typically we will have a lot of unique tokens or unique words in a given collection of text data. So how can we intuitively try and reduce the dimension to a certain extent? Okay, so here are some of the common approaches that are followed as dimension reduction approaches. Some of them are like no-brainers, but and hence they are, almost always done before you deal with any text data. So first one is called uniform casing, which is, if you have the same word in uppercase and lowercase, you do a uniform casing just to, drive home the point that they are the same words and not the different words. Punctuations, you remove punctuations because you'd when you will do tokenization, you will actually break up the entire text data into its most granular meaningful component, and most granular meaningful components are words, right? A punctuation in isolation means nothing. A comma or a question mark in isolation means nothing. So remove the punctuations. Now, if there are digits or numbers, we can either remove them depending on, what kind of use case we are handling, or a better approach is, is to convert them into their word equivalent. So if I have a digit 1, I can basically convert it to ONE, so on and so forth. But in most cases, you can also remove digits. But again, this will depend on the kind of data and the kind of use case you are handling. Then there is, this is interesting. So removing special symbols and separators, because in some case, you will have symbols like at the rate, you will have symbols like hyphen, or you will have other delimiters, and you can have other delimiters in the data. So make sure you are removing them. And then comes uh, the part which actually leads to maximum reduction of dimension of the document term matrix or the document feature matrix, and that is what we remove the stop words. Now, if you see, when we construct a meaningful and a grammatically correct sentence in English, there are lots of parts of speeches which are involved, right? I mean, there are nouns, there are verbs, adjectives, then we have prepositions, articles, so on and so forth. So, but if you think of it from a context or meaning of the sentence perspective, if you strip off all the parts of speeches and just keep the nouns, adjectives, and verbs, even then, you will be able to get or derive the context or the meaning of the sentence. Obviously, the sentence will not remain grammatically correct. It will lose some of the aesthetics, but it will not lose the context or the information or the meaning, right? So what we typically do is when we are dealing with text data, we remove all the parts of speeches or words which are used for grammatical construction of sentence apart from the nouns, adjectives and verbs. So we retain just the nouns, adjectives and verbs, and the other parts of speeches which are required for grammatical construct are removed because they are more required for aesthetics, and even if they are removed, the context or the meaning of the sentence is still preserved. But what do we gain by doing that? Again, that's fairly intuitive. Uh, when we were discussing the concept of document term matrix or the document feature matrix, one of the things that we said was that the number of columns of that matrix is equal to the number of unique words that we have encountered in the entire collection of data. So if we remove uh, everything apart from the nouns, adjectives and verbs, then we significantly cut down on the number of unique words that we have encountered, and hence we reduce the number of columns of the document term matrix significantly. So that's a major gain. The other thing that we do is called stemming. So stemming is again, I'll give an example. So if you have a word called have and another word called having, so it will, stem or strip off the suffix from having and restore it back to have. So again, beginning, doing. So all these kind of words which are derived by adding a suffix to a parent word. So what stemming does is it basically strips off the suffix and maps it back to the parent word. Once again, this is something that helps us reduce the unique number of words to a certain extent and hence reduce the dimension, right? So that is what stemming does. Lastly, there is something which is called lemmatizing, right? So this is again a piece of code which does all of that. So for the time being, we'll park it. This is over here just for the sake of completeness. We'll do a hands-on on this in the next video. So as I was mentioning, the last part of reducing the dimension of the data is lemmatization. Now lemmatization, uh, I would put it this way, that it's required because often when we do stemming, we might end up losing uh, some of the aesthetics from the sentence. So we have already lost a significant part of the aesthetics by stripping off every parts of speech, every other component apart from the nouns, verbs, and adjectives. Now, while we are doing the stemming by removing the suffix from the parent word and then mapping it back to the parent word, we might end up losing some more aesthetics here. So, for example, a word saw, if we do a stemming, it might just return the word s, right? Which would mean nothing. So lemmatization is typically done after stemming, or I would rather say, iteratively while stemming, in order to ensure that while we are stripping off the suffix of a word to map it back to the parent word, we are not reducing the word to something which is meaningless. So stemming will strip off the suffix of the word and map it back to the parent word. But lemmatization will also ensure that this operation does not render the word meaningless. So, so basically, lemmatization adds to the aesthetics of the result, uh, so ensuring that we are working with words which are grammatically correct, the spellings are grammatically correct, but otherwise lemmatization typically will not impact the result of the analysis to a significant extent, but it will just ensure that we are working with words or tokens which are grammatically correct. Okay, so that brings us to the end of the the initial section where we have looked at how we can organize text data in a form that is more familiar to us, at least from our experience of handling numeric or categorical data. And then we have looked at some of the very intuitive challenges of that kind of representation, so the dimensionality problem of the document term matrix. And then we have looked at some very basic approaches to deal with that dimensionality problem and how we can reduce the dimension significantly by following certain steps which are very intuitive and which are kind of no-brainer steps. So in the next video, what we will do is we will do a R implementation of these steps. So we will read the data into the R environment, the Amazon product review data. We will do tokenization, which means we will break up the text data into its most meaningful granular component, which is a word, and then we'll try and construct a document term matrix, see how what a gigantic matrix it turns out to be, and then we'll follow the dimension reduction steps to reduce it to a more manageable dimension. So thank you for watching this video, and see you in the next video where we will do the our hands-on. Thank you. Bye bye.